The Earth's surface, though appearing solid and stable, is in a constant state of motion. Beneath our feet, tectonic plates, massive slabs of rock that make up the Earth's lithosphere, are always shifting, colliding, and sliding past each other. These movements occur at a slow, almost imperceptible rate, driven by the heat from the Earth's core. Over time, stress builds up along fault lines, which are fractures in the Earth's crust where these plates meet. When the accumulated stress exceeds the frictional forces holding the rocks together, the fault slips, releasing a burst of energy in the form of seismic waves. An earthquake is born. To understand earthquakes, one must first explore their anatomy. The point within the Earth where the rupture begins is known as the focus or hypocenter. Directly above it, on the Earth's surface, lies the epicenter, the point where the ground shaking is typically the strongest. The energy released from the focus travels outward in all directions as seismic waves. These waves come in different forms. 1. Primary, P, waves. The fastest seismic waves, P waves, travel through both solids and liquids. They move in a compressional motion, pushing and pulling the ground as they go, much like a slinky toy. Due to their speed, they are the first waves detected by seismographs and the first to reach the surface during an earthquake. 2. Secondary, S, waves following P waves. S waves move slower and can only travel through solids. They move the ground up and down or side to side, causing more damage than P waves. Because they cannot pass through liquids, S waves are not detected in areas separated from the earthquake by the Earth's liquid outer core. 3. Surface waves. These waves travel along the Earth's surface and are slower than both P and S waves, but they cause the most destruction. There are two main types: love waves, which move the ground side to side, and Rayleigh waves, which create a rolling motion, similar to ocean waves. Surface waves cause the ground to twist, turn, and fracture, leading to the visible and often catastrophic effects associated with earthquakes. Earthquakes are closely linked to faults, where the Earth's crust is fractured. There are three primary types of faults, each associated with different tectonic processes. 1. Normal faults occur where two blocks of the Earth's crust are pulled apart. The hanging wall drops relative to the footwall, creating a fault escarpment. These faults are common in regions where the Earth's crust is being extended, such as rift valleys or mid-ocean ridges. 2. Reverse, thrust, faults form where two blocks are pushed together, causing the hanging wall to rise over the footwall. This is typical in regions where tectonic plates are converging, like the boundaries between the Indian and Eurasian plates, where the Himalayas are being thrust upwards. 3. Strike-slip faults. These faults occur where two blocks of the crust slide past each other horizontally. The San Andreas Fault in California is a famous example of a strike-slip fault, where the Pacific and North American plates grind against each other. Each type of fault generates earthquakes with unique characteristics. Normal faults often produce moderate earthquakes, while reverse faults, especially those associated with subduction zones, can produce some of the largest earthquakes in history. Strike-slip faults can generate both small, frequent tremors and powerful quakes that release massive amounts of energy. For decades, the Richter scale was the standard for measuring earthquake magnitude, a logarithmic scale where each whole number increase represents a tenfold increase in amplitude and roughly 31.6 times more energy release. However, the Richter scale has limitations, especially for large quakes, and is less accurate for earthquakes beyond a certain size or at varying distances from the epicenter. Today, seismologists use the moment magnitude scale, MW, which provides a more comprehensive measure of an earthquake's size by considering the amount of fault slip, the area of the fault surface that slipped, and the rigidity of the rocks involved. This scale offers a more accurate assessment of the energy released by an earthquake, making it the standard for modern seismology. Earthquakes are also described by their intensity, which measures the effects of shaking on people, buildings, and the natural environment. The modified Mercalli intensity scale ranges from I, not felt, to XII, total destruction, providing a subjective but vital account of an earthquake's impact on human societies. To fully grasp the power of earthquakes, one must look at real-world examples that have reshaped landscapes and societies. The 1906 San Francisco earthquake, with an estimated magnitude of 7.9, tore through California's San Andreas Fault, triggering fires that razed much of the city. It led to groundbreaking studies in seismology, influencing modern building codes and urban planning. The 2011 Tohoku earthquake in Japan, a magnitude 9.1 quake, was the most powerful ever recorded in Japan and one of the top 5 worldwide. It shifted the Earth on its axis, moved Honshu, Japan's main island, 2.4 meters to the east, and caused a devastating tsunami. The aftermath saw a global reassessment of nuclear safety and emergency preparedness, demonstrating how one earthquake can have worldwide consequences. Earthquakes are more than mere geological phenomena. They are dynamic forces that shape our world, challenge our understanding, and remind us of the ever-changing nature of our planet. As we continue to study these powerful events, we uncover more about the mysteries hidden within the Earth's crust and learn how to coexist with these tremors of creation. Throughout history, earthquakes have repeatedly demonstrated their ability to devastate human settlements, reshape landscapes, and alter the course of societies. They strike without warning, often leaving a trail of destruction and suffering in their wake. Yet, they have also inspired resilience, adaptation, and innovation. This chapter takes a journey through time, highlighting how earthquakes have influenced human civilization, from ancient times to the modern era, by reshaping cities, altering societal structures, and driving advancements in engineering and urban planning. In ancient times, earthquakes were often seen as the wrath of gods or the result of supernatural forces. The Greeks believed Poseidon, the god of the sea, wielded his trident to cause earthquakes, earning him the title Earthshaker. Similarly, in Japanese mythology, earthquakes were thought to be caused by a giant catfish named Namazu, who lived in the mud beneath the islands. Ancient civilizations often wove these powerful natural events into their mythologies to make sense of the destructive force they could not understand or predict. The ruins of ancient cities like Pompeii and Herculaneum, buried under ash and rock from Mount Vesuvius in AD 79, stand as stark reminders of how earthquakes often accompany volcanic eruptions, amplifying the destructive power. In 365 AD, an earthquake in Crete, estimated at a magnitude of 8.0, caused a massive tsunami that devastated cities across the eastern Mediterranean. This event is recorded in both Roman and Greek texts, highlighting how these disasters were often chronicled with awe and fear. Earthquakes did not just destroy, they also forged new beginnings. The city of Lisbon, Portugal, was almost completely destroyed by a massive earthquake on November 1, 1755. This quake, estimated to be between 8.5 and 9.0 in magnitude, triggered fires that burned for days and a tsunami that swept away coastal villages. The disaster profoundly influenced Enlightenment thinkers like Voltaire, who used it to question the nature of divine providence. The rebuilding of Lisbon under the Marquis of Pombal introduced the world's first anti-seismic building codes, an early attempt to mitigate earthquake damage through architecture. The 20th and 21st centuries have seen some of the most devastating earthquakes in recorded history, impacting densely populated urban areas with catastrophic results. The 1906 San Francisco earthquake, striking at a magnitude of 7.9, nearly leveled the city. The quake ruptured the San Andreas Fault for over 296 miles, 477 kilometers, and triggered fires that caused over 80% of the damage. The disaster led to groundbreaking advancements in earthquake science, marking the beginning of modern seismology. It also prompted the development of new building codes and fire safety regulations, which have since been implemented in earthquake-prone regions worldwide. In 1995, the Great Hanshin earthquake struck the city of Kobe, Japan. This magnitude 6.9 earthquake caused the collapse of buildings, bridges, and highways, killing over 6,000 people and injuring more than 40,000. The disaster exposed flaws in Japan's existing construction practices and emergency response systems, leading to substantial revisions in building codes, the introduction of new engineering techniques, and the creation of one of the most comprehensive earthquake early warning systems in the world. One of the deadliest earthquakes in recent memory occurred on January 12, 2010, when a magnitude 7.0 earthquake struck Haiti, near the capital city of Port-au-Prince. The quake killed an estimated 230,000 people, injured hundreds of thousands more, and displaced over 1.5 million. Haiti's vulnerability was amplified by poorly constructed buildings, lack of preparedness, and limited resources. The international response was massive, highlighting both the need for global cooperation in disaster relief and the importance of building resilience in earthquake-prone regions. Beyond the physical destruction, earthquakes leave a profound psychological impact on survivors. The immediate aftermath is often marked by chaos, fear, and uncertainty. Survivors experience a range of emotions, from shock and disbelief to anxiety and trauma. Many suffer from post-traumatic stress disorder, PTSD, experiencing flashbacks, nightmares, and a constant state of heightened alertness. These psychological scars can persist long after the physical wounds have healed, affecting individuals, families, and entire communities. However, earthquakes also bring out extraordinary resilience. Communities often come together in the face of disaster, displaying acts of solidarity, courage, and selflessness. In Kobe, Japan, following the Great Hanshin earthquake, citizens organized themselves into volunteer brigades to rescue those trapped in the rubble, distribute food and water, and provide emotional support. This phenomenon, known as disaster altruism, highlights the innate human capacity to adapt, rebuild, and find meaning even amid catastrophe. In some cases, the aftermath of an earthquake has led to long-term societal changes. For instance, the 2008 Sichuan earthquake in China, which killed around 87,000 people, prompted the Chinese government to re-evaluate its approach to disaster management. It invested heavily in rebuilding infrastructure, developed comprehensive emergency response protocols, and improved public awareness campaigns. These efforts reflect a broader understanding that resilience is not just about surviving the quake itself, but also about fostering a culture of preparedness and learning from past mistakes. Earthquakes have historically driven advancements in engineering and urban planning. To withstand the forces of nature, civilizations have innovated over the centuries. The ancient Inca city of Machu Picchu in Peru, for example, features structures built with precisely cut stones that fit together without mortar, allowing them to move slightly during an earthquake and remain intact. This technique, known as ashlar masonry, reflects an early understanding of seismic resilience. In modern times, architects and engineers use cutting-edge technologies and materials to construct earthquake-resistant buildings. Skyscrapers in cities like Tokyo and San Francisco are equipped with base isolators, which allow structures to move independently from the ground, shaking, and dampers, which absorb and dissipate seismic energy. The Burj Khalifa in Dubai, the tallest building in the world, features a unique Y-shaped design that helps it withstand lateral forces, including those from earthquakes. Urban planning has also evolved in response to earthquake risks. In Istanbul, Turkey, a city built atop several fault lines, officials have initiated comprehensive retrofitting programs to strengthen older buildings. In Los Angeles, new laws require the retrofitting of vulnerable structures, such as soft-story apartments and non-ductile concrete buildings, to withstand future quakes. These efforts reflect a growing recognition that proactive planning and innovative engineering are essential to reducing earthquake risks. Earthquakes do not respect borders, and their impacts are felt worldwide. In an increasingly interconnected world, there is a greater need for international cooperation and shared knowledge. Global organizations like the United Nations Office for Disaster Risk Reduction, UNDRR, and the World Bank work to promote resilience through initiatives such as the Sendai Framework for Disaster Risk Reduction, which emphasizes the importance of understanding risk, strengthening disaster governance, investing in resilience, and enhancing disaster preparedness for effective response. The chapter closes by reflecting on the dual nature of earthquakes, as agents of destruction and as catalysts for progress. From ancient myths to modern science, they have shaped human civilization in profound ways, driving us to adapt, innovate, and prepare for an uncertain future. While earthquakes may be inevitable, their impact is not, and humanity's ongoing quest to mitigate their effects speaks to our enduring spirit of survival and resilience. As humanity's understanding of earthquakes has grown, so too has the science dedicated to studying these powerful natural phenomena. The field of seismology, the study of earthquakes and the propagation of seismic waves through the Earth, has evolved from rudimentary observations into a sophisticated discipline that employs cutting-edge technology and complex mathematical models. This chapter delves into the scientific breakthroughs that have transformed our understanding of earthquakes, the tools and techniques seismologists use to study them, and the ongoing challenges in predicting these unpredictable forces of nature. The earliest attempts to study earthquakes were largely observational, with ancient scholars documenting the damage, duration, and effects of tremors. In the 2nd century AD, Chinese philosopher Zhang Heng invented the world's first known seismoscope, a device that could detect the occurrence of an earthquake, even at a distance. Heng's bronze urn-like instrument was ingeniously designed with a pendulum mechanism that, when shaken by an earthquake, would drop a ball from the mouth of a dragon into a corresponding frog, indicating the direction from which the tremor originated. Though primitive by today's standards, Heng's invention marked a significant step towards understanding and detecting earthquakes. Fast forward to the 19th century, and the field of seismology began to take shape as a formal science. In 1880, the invention of the seismograph by British scientists John Milne and Thomas Gray provided a new way to record seismic waves. The seismograph could measure ground motion during an earthquake, providing valuable data that allowed scientists to begin quantifying the intensity and duration of earthquakes. By the 20th century, seismology was revolutionized by the development of more sensitive instruments and the advent of digital technology. The discovery of tectonic plates and the theory of plate tectonics in the 1960s provided a unifying framework for understanding the mechanics of earthquakes. Seismologists realized that most earthquakes occur along the boundaries of these moving plates, where the Earth's lithosphere is subjected to intense stress and deformation. Modern seismology relies on a wide array of tools and technologies to study earthquakes in unprecedented detail. The seismometer, an advanced version of the seismograph, remains the primary instrument for detecting and recording ground motion. Seismometers are strategically placed around the world, forming a global network that monitors seismic activity continuously. These instruments can detect even the faintest tremors, allowing scientists to map earthquakes with remarkable accuracy. GPS technology has also become an essential tool in earthquake science. High-precision GPS stations are installed near fault lines to measure the slow movements of tectonic plates over time. By tracking the buildup of strain along faults, scientists can estimate where stress is accumulating and identify areas at risk of future earthquakes. For example, GPS data have helped pinpoint the areas of increased risk along the San Andreas Fault in California and the Himalayan region, where the Indian plate collides with the Eurasian plate. Satellite-based remote sensing adds another dimension to earthquake research. Using radar and optical imagery, satellites can detect ground deformations caused by earthquakes with millimeter-level precision. Techniques such as interferometric synthetic aperture radar, INSAR, allow scientists to visualize how the ground moves during and after an earthquake, providing critical data on fault behavior and helping to improve models of seismic hazards. Seismic tomography is another cutting-edge technique, akin to a CT scan for the Earth. By analyzing how seismic waves generated by earthquakes travel through different layers of the Earth, scientists can create three-dimensional images of the planet's interior. This method reveals the structure and composition of the Earth's crust and mantle, offering insights into the conditions that give rise to earthquakes and volcanic activity. At its core, an earthquake is a process of faulting, where rocks on either side of a fault line suddenly slip past each other. To understand this process, scientists examine the stress and strain acting on rocks in the Earth's crust. Stress refers to the force per unit area exerted on a material, while strain is the deformation or change in shape that occurs as a result of that stress. There are three main types of stress that contribute to faulting. 1. Tensional stress pulls rocks apart, causing them to stretch and elongate. This type of stress is common at divergent plate boundaries, where tectonic plates move away from each other. 2. Compressional stress pushes rocks together, causing them to shorten and thicken. This stress is prevalent at convergent plate boundaries, where plates collide. 3. Shear stress acts parallel to a fault plane, causing rocks to slide past each other. Shear stress is typical of transform plate boundaries, where plates grind horizontally against each other. When stress accumulates to a point where it exceeds the strength of the rocks, the fault ruptures, releasing energy in the form of seismic waves. This process can be modeled mathematically using elastic rebound theory, first proposed by geologist Harry Fielding Reid after the 1906 San Francisco earthquake. According to this theory, the Earth's crust behaves elastically, like a stretched rubber band, storing energy until it reaches a breaking point, at which it snaps back, releasing the stored energy as an earthquake. The study of frictional properties of rocks along faults has also shed light on earthquake dynamics. Experiments have shown that some faults are stick-slip faults, where rocks alternately stick together and then slip suddenly, while others experience creep, where rocks move steadily without generating significant earthquakes. Understanding these behaviors is critical for assessing earthquake risks, especially in heavily populated areas. Despite advances in seismology, predicting earthquakes remains one of the greatest challenges in earth sciences. Unlike weather forecasting, which benefits from continuous data collection and a clear understanding of atmospheric dynamics, earthquakes occur deep within the Earth, beyond direct observation. Currently, scientists can estimate the probability of an earthquake occurring in a given area over a certain period based on historical patterns, fault activity, and the accumulation of stress, but they cannot predict the exact time, location, and magnitude of an earthquake with any certainty. For instance, while scientists know that the San Andreas Fault in California is due for a significant earthquake, they cannot predict precisely when it will happen. Research is ongoing to develop more reliable methods of earthquake forecasting. One area of interest is the study of earthquake precursors, or phenomena that might signal an imminent earthquake, such as unusual patterns of seismicity, changes in groundwater levels, or strange animal behavior. However, these signs have proven inconsistent and unreliable, often leading to false alarms or missed predictions. Machine learning and artificial intelligence, AI, offer new hope for earthquake prediction. By analyzing vast amounts of seismic data, AI algorithms can identify patterns and correlations that may elude human analysts. For example, AI has been used to detect small earthquakes that might otherwise go unnoticed, providing a clearer picture of how seismic activity evolves over time. However, this field is still in its infancy, and much work remains to be done to achieve reliable earthquake prediction. While predicting earthquakes remains elusive, significant progress has been made in mitigating their impact. Modern earthquake early warning systems can detect the initial, less destructive P waves of an earthquake and send alerts seconds to minutes before the more damaging S waves arrive. These alerts can automatically shut down gas lines, stop trains, and give people precious moments to take cover. The development of these systems relies heavily on global cooperation and data sharing. Countries like Japan, Mexico, and the United States have invested in extensive seismic networks that provide real-time data for early warning systems. These efforts underscore the importance of international collaboration in reducing the risks posed by earthquakes. Looking ahead, earthquake science will continue to evolve, integrating new technologies, expanding data collection efforts, and refining models of seismic risk. The goal is not only to understand the forces that drive earthquakes but also to build a society that is resilient to their inevitable occurrence. This involves not just technological advancements but also fostering a culture of preparedness and awareness. As seismologists unlock more secrets about earthquakes, they are reminded of the complexity and unpredictability of these natural events. While it may never be possible to predict precisely when an earthquake will occur, our understanding of their mechanisms, effects, and risks continues to grow. With this knowledge, we can better prepare for the inevitable and strive to build a world that is not only aware of the forces beneath our feet but also resilient to their sudden and sometimes devastating eruptions. For millions of people worldwide, earthquakes are more than just natural phenomena, they are a constant, looming threat. Entire cities, from Los Angeles to Tokyo, Mexico City to Kathmandu, sit atop tectonic boundaries where the risk of earthquakes is ever present. This chapter explores human vulnerability in these earthquake-prone regions and the remarkable resilience communities demonstrate in preparing for, responding to, and recovering from seismic disasters. Through stories of past earthquakes, we'll examine what makes certain areas more vulnerable than others and how urban planning, architecture, community engagement, and technological innovations can reduce the risks and enhance resilience. Earthquake vulnerability is shaped by a combination of geological, geographical, and socio-economic factors. Some regions, like the Pacific Ring of Fire, experience frequent seismic activity due to their location along tectonic plate boundaries. Cities built near these boundaries are inherently at higher risk of earthquakes. But while the geological risk is constant, the impact of an earthquake is highly dependent on human factors, such as population density, building practices, and economic development. For instance, in 2010, Haiti experienced a devastating earthquake with a magnitude of 7.0. Despite the earthquake being relatively moderate, it caused massive destruction, killing over 200,000 people and displacing millions. The high death toll and damage were primarily due to poorly constructed buildings, a lack of enforcement of building codes, inadequate emergency response infrastructure, and the socio-economic vulnerability of the population. In contrast, the 2011 Tohoku earthquake in Japan, which was much stronger at a magnitude of 9.1, resulted in far fewer casualties relative to its size, thanks to Japan's strict building codes, early warning systems, and robust disaster preparedness programs. One of the most effective ways to mitigate earthquake damage is through careful urban planning and resilient building design. Cities in earthquake zones have increasingly adopted earthquake-resistant construction techniques to minimize the risk of building collapse. Modern engineering solutions, such as base isolation systems and damping technology, help buildings withstand seismic forces. Base isolation involves placing a building on flexible bearings that absorb and dissipate seismic energy, while dampers are devices that act like shock absorbers, reducing the amplitude of building vibrations during an earthquake. In addition to technological solutions, the design of buildings and urban spaces plays a crucial role. Open spaces such as parks and public squares can serve as evacuation points during earthquakes, while wide streets and grid patterns can help emergency services reach affected areas more quickly. Incorporating earthquake resilience into urban planning involves not just the physical design of structures, but also the creation of community resources, such as public awareness campaigns, earthquake drills, and emergency response plans. However, implementing these measures is often easier said than done, especially in low-income countries or densely populated urban centers. In many developing nations, the cost of retrofitting existing buildings or enforcing strict building codes can be prohibitively high, and a lack of political will or public awareness may further complicate efforts. Nonetheless, international organizations, NGOs, and governments are increasingly collaborating to bring earthquake resilience to vulnerable communities, advocating for policies that prioritize safety and preparedness. Community preparedness is a cornerstone of earthquake resilience. While technological advances and urban planning efforts are critical, they must be coupled with community engagement and education to be effective. In places like Japan, community preparedness is a cultural norm. Regular earthquake drills, early warning systems, and public education campaigns have fostered a culture of readiness. Every citizen, from children to the elderly, knows the basics of earthquake safety: drop, cover, and hold on. Elsewhere, however, preparedness varies widely. In many regions, a lack of resources, education, or awareness can leave communities unprepared for a major earthquake. Organizations like the Red Cross and the United Nations Office for Disaster Risk Reduction, UNDRR, work to fill these gaps by promoting risk awareness, conducting training sessions, and distributing emergency supplies. Grassroots organizations also play a vital role, empowering local communities to develop their own disaster response plans tailored to the unique risks and needs. Advances in technology have revolutionized the way we prepare for and respond to earthquakes. Earthquake Early Warning Systems, EEWS, which detect the initial P waves of an earthquake and send out alerts before the more destructive S waves arrive, have saved countless lives. In countries like Japan and Mexico, these systems provide precious seconds to take cover, halt transportation, shut down critical infrastructure, and mobilize emergency services. Beyond early warnings, big data and artificial intelligence, AI, are being harnessed to improve earthquake resilience. AI can analyze patterns in seismic data to refine risk assessments, predict aftershocks, and optimize emergency response efforts. Mobile apps and digital platforms enable real-time communication during disasters, helping to coordinate rescue efforts and disseminate critical information to affected populations. Human resilience in the face of earthquakes is evident in the stories of communities that have not only survived but thrived after seismic disasters. Consider the case of Christchurch, New Zealand, which was struck by a series of devastating earthquakes in 2010 and 2011. Despite significant loss of life and damage to infrastructure, the community came together to rebuild a safer, more sustainable city. Innovative architectural designs, a renewed focus on public spaces, and a spirit of collective resilience have transformed Christchurch into a model of post-disaster recovery. Similarly, the 1995 Kobe earthquake in Japan prompted sweeping reforms in disaster management, urban planning, and building regulations, which have since been adopted worldwide. These experiences underscore the capacity of communities to adapt and rebuild, turning tragedy into an opportunity for growth and improvement. As the global population continues to grow and urbanize, more people than ever are living in earthquake-prone regions. The future of earthquake preparedness will depend on our ability to anticipate and adapt to new challenges, from climate change and urbanization to technological advancements and evolving societal needs. This final chapter looks to the future, exploring the strategies, innovations, and collaborative efforts needed to build a resilient world in the face of earthquake risks.